So it's time now to model pipes, which are very important for flow rates and also to calculate pressure drops. Now, this is very important, especially when we are changing flow rates, because when we change flow rates, we change velocities of the materials, and when we change velocity of the materials, the Reynolds number is changed, which directly implies that the friction is being changed. Okay, so essentially, if we change flow rates, we are changing friction factor or overall pressure drop. Okay, so let's model the pressure drop in piping system of steam using steam tables. These are the conditions, and we're going to model two types, schedule 80 and schedule 40, 1 inch, 2 inch, and these total lengths. Let's go here, water, the water steam tables, and what I want to do is first let me add the feed. $80 psi and 1,000 kilogram, 10,000 pure. Now add the manipulator, because we're going to be using plenty of streams. Let these wait. So this is pipe. So this will be the 1 inch 40 scheduled pipe, 2 inch 40 scheduled pipe, 1 inch 80 scheduled pipe, 2 inch 80 scheduled pipe. Add the feeds. So 140, 240, 180, and 280. Okay guys, so we have the same flow rates, and we're going to be changing the total length. We're going to be using carbon steel, schedule number 40. Nominal diameter is 1 inch. So it is awesome that all other data will be calculated. The same here, 15 meters, total inch size. No, this is the 40 schedule 2 inch pipe. This might be a little bit tedious, but it must be done. And imagine a set of pipelines or a very complex set of piping systems. This will be definitely not that nice, especially if you have also elevations, piping angles, different roughness, and so on. So this run is for 50,000, so let me add that. Okay, so let's run. Okay, so there are several warnings. Okay, so we need to state the phases apparently. So let's assume all these are adiabatic, meaning that we're not adding any external heat. Run again, and we're done. There are no more errors, no warnings. Okay guys, so let's analyze what's happening here. There's a pressure drop. Okay, so here's the pressure drop. It goes from 6, wait for it, because we are using bar, it's 6 psi. We know this is 80 psi, 6 bar. So it drops from 6 to 4, 6 to 5, 6 to 3, and 6 to 5. Okay, so apparently this is the greatest pressure drop, essentially because the same size but higher schedule will imply that the inner diameter is decreasing. Therefore, the velocity increases, which requires a pressure drop. Okay, so that seems nice. Let's now change this. So I'm going to copy all these. Let's go here. L30. It's third L. Okay, so let me fix this right here. This will be my view number 1, and this will be my second view. Oops, apparently we didn't have copy here. Okay, so this is going to be 30 meter. Let me adjust this for convenience. And let's now change all the lengths twice. Run the simulation. No errors, no warnings. So now let's check out. Apparently we are having some errors. Look here, wait. So the vapor fraction here is pure liquid. Goes here. 6 to 2, so there is much greater pressure drop, actually almost twice as in this one right here. So we got 4, and in 30 meters we get this one right here. So what else do we have here? We are having a total pressure drop here. So what's going to happen is that you're going to increase a pressure. You need to increase the pressure, so you need to add a pump because there is no more pressure to push the water, which is very interesting how it is the one with the greatest pressure drop until eventually you will need to add a pump to continue this flow rate. So this way we can change length, pressures, data on the pipes, materials, and so on. So it's very interesting how we can, maybe you didn't expect this pressure drop, this drastic pressure drop in a 30 meter length. Well, there you have a 6 bar pressure drop.